Hi, and welcome to video 3 of 3 for Chapter 5. Now, in the previous two videos, we discussed the Coulomb force. That is the electrical force that sits between things that have charges. And we also looked at the electric field. Um, now, I mentioned previously, actually in the second video, that when you have a large number of charges, instead of using discrete single point charges and then summing up to find electric fields and things like that, what you do is you extend your sum to an integration. Now, what I'm going to do today is to do a number of these integrals dealing with continuous distributions of charge. Now, my primary goal here is twofold. The first thing I need you to see is how these integrations are done. They may or may not be of use in this class directly. However, in future classes that you might take, the tricks and the tools that we use here will probably prove to be pretty useful. The second reason is because the results of these integrations are incredibly useful to us. For example, a line of charge is very close to being a line of current, which we'll be talking about when we talk about magnetism. Sheets of charge are what we see inside devices called capacitors that allow us to store electrical energy. So the results from these integrations are very useful to us from an electricity standpoint. Now, that said, I'd like to remind you of a few of the integrals that we had written down last time. Specifically, if you're dealing with a line of charge or a curve of charge, the electric field at some given point r looks like 1 over 4 pi epsilon naught, the integral over the line of lambda dl prime over r minus r prime cubed r minus r prime as a vector. Now, the one for area, 1 over 4 pi epsilon naught, the integral over area. Now, this is your charge, your area charge density, dA prime, r minus r prime, divided by r minus r prime cubed. For a volume, again, 1 over 4 pi epsilon naught, the integral over a volume of rho dV prime, r minus r prime divided by r minus r prime cubed. So, again, this is for an area, and this is for a volume. So, we're primarily going to be using this one today. We will use this one as well, but primarily we're going to be using the line one, and you'll see why. So, the first example that I want to take a look at deals with the electric field above an infinite length of charge. Now, this line of charge goes from minus infinity to plus infinity. And the fact that it is a line of charge tells us exactly which one of these we need to be using. We should use this equation right here to calculate whatever the electric field would be at this point right here. So, this is the equation we're going to use. Oh, that should be dl prime. Sorry about that. Now, let's talk about what our vectors are in this case. And to do that, what I want to do is to look at this little chunk of charge here that I'm going to call dq. Now, ultimately what we're going to be doing is to be summing all the way from minus infinity to plus infinity. But at this point right here, let's just look at the effect of this one. It's going to have an electric field at this point that's going to point in that direction right there. Okay? So if you take a look at this vector right here, this would be the same thing as this right here, r minus r prime. Okay? So what would r prime be? Well, r prime is the distance from the center of our coordinate system to wherever our charge is located. And our charge is located along the x-axis. So it is going to be at x prime, x hat. Now x prime is going to run from minus infinity to plus infinity as we add up all of the effects of the electric field. Now, this right here, this is r. So just to sort of point things out, and I'm going to use a different color for this. I'll use purple. This right here is r prime, and this right here is r. So r here is going to be y above the x-axis. Okay? So as you can see, if you go back and you look at the previous video, this right here is r minus r prime. This plus this, or this minus this rather, is equal to this right here. So what's the length of this? X prime squared plus y squared, using the fact that this is a right angle and we can use the Pythagorean theorem on it. Okay? Now, so we have our vectors here. We're going to assume our charge density is constant. It's just however much charge there is over length. So it's going to be constant. If it's not, we need to know what form it has so we can actually perform the integration. And let's plug this stuff into our integral here. So e here, and let me be entirely precise about this as a function of r, is 1 over 4 pi epsilon naught times the integral over. Now what's our length? Well, we're going from minus infinity to plus infinity. Lambda is a constant. dl prime here is our line. That's going to be dx. That's the curve that our charge sits on, is the x-axis. R minus r prime, well, I mean, r is y hat. R prime is x prime x hat. In the denominator, we have the length of r minus r prime squared. That's this right here. That's this distance. Now, or this cube rather. Now the length is this, so we have to cube it, which makes it to the 3/2 power. Now this is the integral that we need to do, and depending upon where you're at in Calculus 2, if you've had it before, who your teacher is, where you took it, etc. and so on, you may or may not have seen integrals like this. Now, first of all, this is actually two integrals, and that's because we have one part that sits along the y-hat direction and one part that sits along the x-hat direction. So let's just go ahead and break that up into two pieces. That's going to be 1 over 4 pi epsilon naught. And actually, I tell you what, instead of saying 1, I'm going to go ahead and pull out lambda because that's constant. Lambda over that. Now, what's left that we have to integrate over is the first part, which deals with y and that's again dx prime. And then we have the second part, which deals with x. So these are our two integrals that we're going to do. And I'm going to call this number 1 and this number 2. So let's start off with number 1, which is the part that lies along the y-hat direction. So number 1 looks like this. Now, conveniently enough, y and y prime are both constants. Not y prime, rather, but y hat. Y hat's just a unit vector, and in the Cartesian coordinates, x, y, and z are constants. So they're not something that has anything of value on the inside that we can integrate. Likewise, y is just how high above we are. It's just a number, so it's a constant. So I can pull those things out. So the integral that we really want to do is this right here. Now, to do this integral, I'm going to do a change of variable. And what I want to do is to clean this up a little bit. And the approach that I want to take is to call x prime y tangent of theta. Now, whenever you see this sorts of stuff in the denominator, trig substitutions end up being some of the more useful things here. Now, that said, if you take a look here, if you make this type of association, what you've done is you've sort of used trigonometry and you've created a right triangle. So, for example, and I'm just going to go ahead and draw my right triangle out here. If I called this right here theta, okay, and you think of what tangent is opposite over adjacent. So the opposite side here would be x prime. The adjacent side would be y, because when you move that over there, it goes into the denominator. And the hypotenuse here would be x prime squared plus y squared. Now, this may or may not be useful to us later on as we go through the problem. But it's good to trace these things out, because what this does is to give us the ability to go between this representation of our integral and the change of variable that we made. In this particular problem, I don't think it's very useful, but in the next one that we do, it is going to be very useful. So, that said, if I take and I plug this in, noting the fact that the derivative of x prime here, or the differential rather of x prime here, would be y times secant squared of theta d theta, because that's the derivative of tangent. If I plug that into here, I have y hat, the integral from, and we're going to talk about the limits of this integration here in a second. I have a dx prime here on the top. The dx prime is y secant squared of theta d theta. In the bottom, the denominator, I have x prime squared. X prime is this. And then I have a plus y squared, and that's raised to the 3/2 power. Okay. Now, what I'd like to point out here is the following. Again, y is just a constant. It's just a height. So I can pull that out here, and that would make this a y squared. But if you look at what's going on in the denominator here, there's a y squared here, and there's a y squared here. I want to pull these out. Now, when I do that, though, I'm raising y squared to the 3/2 power. Now, the half part is going to take the square part and make that be 1, which means that I'm stuck cubing it. So when I pull that out, that becomes a y cubed. I'll have a y squared on the top. I'll have a y cubed on the bottom. And when you actually cancel things out, you have a 1 over y. Now, what about my limits of integration? Well, we're going from minus infinity to plus infinity. And I've chosen to use a substitution that has a tangent. Now, if you plot tangent, okay, so let's pretend that this is our angle theta, and this is tangent right here. If you plot it, what you'll discover is that at minus pi over 2 and at pi over 2, your tangent blows up. It looks something like this. It becomes asymptotic. So what that means is that for tangent, if you want theta here to produce a minus infinity, you plug in a minus pi over 2. And if you want theta here to produce a plus infinity, you plug in a pi over 2. So those are our limits of integration now. Okay? So from minus pi over 2 to pi over 2. We've already handled the y's here, which means that we have a secant squared of theta d theta on the top. And on the bottom, we have tangent squared of theta plus 1 raised to the 3/2 power. Now look, if you go back and you take a look at your trig identities, what you'll see there are trig identities that look like this. Sine squared of theta plus cosine squared of theta is equal to 1. And then you'll see another one that goes something like this. Tangent squared of theta plus 1 is equal to secant squared of theta. And that's the reason why I made the substitution. Okay? So really what this is secant squared of theta. Now much like that y, when you take secant squared and you raise it to the 3/2 power, the square and the half kill each other off to give you 1, and you end up cubing it. So you have a secant squared on the top, and you'll have a secant cubed on the bottom. That's 1 over secant of theta. But secant itself is 1 over cosine, which means this is 1 over cosine, or just cosine of theta. So this integral right here is just a cosine. That's the power of trig substitutions. So here, 1 over y hat, integrated from minus pi over 2 to pi over 2, cosine of theta d theta. And that's what we're integrating. Now, the derivative of sine is cosine, which means the antiderivative of cosine is sine. But we have to evaluate this from minus pi over 2 to pi over 2. Now that's pretty easy to do. Let me just write this out. Oh, why am I putting secant in there? Should be sine, right? Not just be technically correct, but there. Now, remember, sine is an odd function, and the way odd functions work is that if you put a minus argument on the inside, you can pull the minus sign out. And when you do that, that makes this a plus. Likewise, sine of pi over 2 is 1, which means at the end of the day, this right here is just 2. So the end result of this integration is 2y hat over y. So that takes care of integral number 1. Now what about integral number 2? Well, integral number 2 looks like this. Here we have a x prime, x hat, dx prime, and in the denominator you have x prime squared plus y squared raised to the 3/2 power. Now, Again, the x prime is a constant, or not the x prime, but the x hat is a constant, rather. So what we're integrating is this. I'm going to use exactly the same trig substitution. So when I do that, my integral here looks like the following. Remember, our limits of integration have changed to minus pi over 2 to pi over 2. X prime is now y tangent of theta. Dx prime is y secant squared of theta d theta. And into the denominator over here, just like before, we have y squared tangent squared of theta plus y squared raised to the 3/2 power. Now, as you can see here, you have two y's here. When we handle the y's down here, you'll have 3 of them down there. That will be x hat over y. Our integral from minus pi over 2 to pi over 2 now looks like this. Now again, remember, this ends up being secant cubed, right? You have a secant squared here, you have a secant cubed here. This will cancel out all but one of those, leaving you a tangent of theta over secant of theta that you have to integrate. Now you might look at that and say, oh no, this is going to be a problem. But look, tangent is sine over cosine. Secant is 1 over cosine, which means that this is just a sine. Okay, so our integral here is going to be x hat over y, the integral from minus pi over 2 to pi over 2, sine of theta d theta. Now look, the derivative of sine we know is cosine. The derivative of cosine is minus sine. So when you take and you do the antiderivative of this, you do the integral, that puts a minus sign out in front. You have an x hat over y, and then you have a cosine of theta that you have to evaluate from minus pi over 2 to pi over 2. So when you do that, it looks like this. Now look, cosine of pi over 2 is 0. Cosine of minus pi over 2 is 0, which means that integral is 0. So here, at the end of the day, I have this stuff sitting out in front. That is lambda over 4 pi epsilon naught. Then, out of these two integrals, the only one that survived is this one right here, the result of which is 2 y hat over y. As you can see, this 2 right here is going to cancel with one of those, giving you a 2 left over in the denominator. And your electric field here is going to be lambda over 2 pi epsilon naught y hat. This is a result that you can write down. I'm going to drop the vector for a moment. This is the electric field magnitude for an infinite line of charge. And this is a good result to have. So you're going to want to box this in your notes and star it. Now, what does this mean? Well, let's take a look at our picture again. And I want to remind you, the goal here was to start at minus infinity and to just sum all the way to plus infinity. Here's the deal, though. For every bit of charge to the left that's, we'll say, 5 meters away, that has an electric field that points this way, there is going to be a bit over here 5 meters away that has an electric field that points this way. And if you remember the previous video where I talked about the electric field that sits between two point charges that have opposite polarities. Now, I showed you that things cancel out. What's happening here is that the side-to-side parts of the electric field are canceling out, and you're ending up with two up parts that add. So here, in two dimensions, the electric field is always going to point up this way if you're above it, and if you're below it, it's going to point down this way. Okay. Now, if you were to extend this to 3 dimensions, what you would have would be a loop that sort of defines a region around your line of charge in which the electric field has the same magnitude. So it would look like that. Oh, how I dropped the Y there. There we go. So, another way you can write this, and you're going to want to box this in your notes as well, is this way. There you go. So, not too bad. So now let's do a little bit more complicated example. This is a finite rod. It has a length of L. That is, if you go from here to here, this distance right here, that's L. What I'm going to do is I'm going to split the rod in half. So this is going to be our point of interest, is at the center point. The reason why I'm picking center points is that as you get further and further away from the center, you have what are called fringe effects, which makes your integration incredibly complicated. We want to avoid that. So that's actually above the pay grade of this particular class, were you to take electricity and magnetism as a course. Usually it's 2 semesters, and you would do this in great detail. So over here, you have minus L over 2. This is this position, and this position right here would be L over 2. So here, our charge density lambda, you could think of as being all of the charge Q that sits along the length of L. So you can actually write that out here. In the previous case right here, it's difficult to write that out since L is infinite. So we're going to be using the same equation. Same one. And again, if you think of starting over here with this little bit of charge dq and go from minus L over 2 to L over 2 that way, then this right here, your r prime vector, which locates from the origin to where your charge is, would equal to x prime x hat, just like before. And the location of our point of interest in the center of the rod would sit up over here, and it would be r, and that's going to be y hat. So what that means is that r minus r prime is simply going to be y hat minus x prime x hat. Okay, so that means we can write down our electric field integral. We're starting from minus L over 2. We're ending up at L over 2 instead of minus infinity to plus infinity. Lambda dx prime, r minus r prime, is y hat minus x prime x hat. In the denominator, we have, just to remind you, this right here is the square root of x prime squared plus y squared. Just like the other one. Same thing here. Raised to the 3/2 power. Okay, so this is the integral that we're going to end up wanting to do. And we're going to take the same sort of path through this, with the exception of how we handle our tangents. In this case, we can't appeal to, tangent at, of minus pi over 2 being minus infinity, and tangent of pi over 2 being infinity. We can't use that trick here because we're not integrating from minus infinity to infinity. Now, typically, in many math classes, what they do is they say, okay, well, you take your inverse tangent, and that ends up being your limits of integration. We're not going to do that. We're going to play a trick using the geometry stuff that I mentioned before. Okay, so let me just go ahead and separate this out, noting again the fact that lambda over 4 pi epsilon naught sits out in front. We have two integrals again. First integral going from minus L over 2 to L over 2 of dx prime y hat over x prime squared plus y squared raised to the 3/2 power minus, again, another integral, minus L over 2 to L over 2 of x prime x hat dx prime over x prime squared plus y squared raised to the 3/2 power. Okay, so these are our integrals again. That's number 1. That's number 2. So let's take a look at the first integral. The first integral looks like this. It's minus L over 2 to L over 2. The y and the y hat come out. Remember, those are constants. We have a dx prime over x prime squared plus y squared raised to the 3/2 power. We're going to do exactly the same substitution that we did before. Okay, so that was, we're going to call x prime y tangent of theta. Dx prime is y times secant squared theta d theta. And now we're going to plug the substitutions in here. Now, I'm going to call my limits here a and b. I'm not going to touch them yet, and there's a reason for that. We're going to see that here in a moment. Let me just go ahead and plug stuff in here. This is y secant squared of theta d theta, that's dx. Here, it's y squared tangent squared of theta plus y squared raised to the 3/2. Okay. And now let's draw our triangle. Based off of our substitution. So, if I call this theta right here, the opposite side is x prime, the adjacent side is y, and the hypotenuse is going to be, x prime squared plus y squared, or vice versa. So we're going to be using this here in a moment. But let's pick up with our integration here. As before, this is y squared, this is a y squared. If I pull it out, it's y squared raised to the 3/2 power, which makes that y cubed. You have a y squared here, meaning that in the front you have y hat over L. Or not L, but y. So, our limits of integration again from a to b. I just want to acknowledge that they're there. We don't know what they are. We're not going to necessarily need them, and you'll see that here in a moment, or at least making the transformation to a new set of them. So as before, again, this, when you turn this into a secant squared, it's secant squared raised to the 3/2 power, which is secant cubed. You have secant squared over here. This whole thing right here ends up being 1 over secant theta, which ends up being a cosine of theta, just like before. So let's go ahead and perform an integration. Again, the derivative of sine is cosine. So this is a sine of theta evaluated from a to b. Now, like I said, in a traditional math class, typically what they would do is they would plug in their limits here, and you would do a arctangent, and that would give you the bottom and the upper limits. I don't want to do that, though. I want to go back to my old limits. And the way I go back to my old limits is having done the integration and having a relationship between theta and the sides. Well, I'm just going to make a sine. Sine of theta is opposite over hypotenuse. The opposite side here is x prime. And the hypotenuse is the square root of x prime squared plus y squared, which means that this is what our integral gave us. Now we're evaluating this over our original limits, minus L over 2 to L over 2. Now, if you take a look here, that's a constant. We have L over 2 divided by the square root of L over 2 squared plus y squared. That's this top limit minus a minus L over 2 divided by the square root of minus L over 2 squared, which is really the same thing as L over 2 squared. That right there. So here you have a minus, which is a plus. You have L over 2 here plus an L over 2 here, which is just L. So this would be y prime L over y times the square root of L over 2 squared plus y squared. Okay, so that's what the first one is. Now, as you can see, this allowed us to evaluate the limits of integration here without having to, seek them in our, in the space in which we substituted, into a trig function. So it actually makes life a lot easier. Now let's do this one right here. So that's minus L over 2 to L over 2. X hat, x prime, dx prime over x prime squared plus y squared raised to the 3/2 power. Now we're doing exactly the same thing here. We're making exactly the same substitution as we did before. In fact, let me just go ahead and snag that pertinent information. Same thing. I'm even going to snag my my geometry here because we'll need it. Now here, x hat comes out. It's minus over 2, L over 2 here. We have an x prime, dx prime, divided by x prime squared plus y squared raised to the 3/2 power. And let's just go ahead and plug in our stuff. We have our substitution again. Actually, let me drop those limits of integration. Got a little bit ahead of myself there. Just again, a to b to acknowledge the fact that that they're there, but we're going to have to find them. This y tangent of theta dx prime is y secant squared of theta d theta. Here in the denominator, you have x prime, which is y squared tangent squared of theta plus y squared raised to the 3/2. And the same as before. You've got 2 y's here. You've got 3 y's in the bottom. That gives you a y in the bottom. So and again, this becomes a secant squared of theta. You raise that to the 3/2 power. It's secant cubed. This is secant squared. And as we argued out earlier, this really is just sine. Okay? So we're integrating this. Well, the derivative of sine is cosine. The derivative of cosine is minus sine, which means that when you do the antiderivative for sine, it's a minus sign out in front. Gives you a cosine. But now look at our picture here. Again, over the angle that we've defined using trig, cosine is adjacent over hypotenuse. The adjacent side here is y. The hypotenuse is the square root of x prime squared plus y squared. So now we can transition back to our old limits of integration without having to deal with any nonsense. And so this is what we're dealing with. We've got a y over the square root of x prime squared plus y squared, evaluated from minus L over 2 to L over 2. The y's cancel. This minus this, so 1 over the square root of L over 2 squared plus y squared. That's the top limit. Minus 1 over the square root of, this is x prime squared. This is negative, sure, but when you square it, it becomes positive. So you can just drop the negative on the inside. That's 0. And again, that should make sense because what's left is just the y part. For every bit of charge we have to the left, that gives us a field that points this way. We have a bit of charge to the right that gives us a field that points this way. So the x parts of the field cancel, giving us just the y part. So at the end of the day, here, our electric field is going to look like lambda over 4 pi epsilon naught times this right here. Okay. Now, just to remind you, if you think of there being a total charge of Q distributed over the length of this thing, and you think of the relationship between these two as being this, then lambda times L is just Q. So you can write this as Q over, or Q y hat over y times the square root of L over 2 squared plus y squared. Now, if you made the transition to circular polar coordinates, like what we did, say here, and you think of r as being the distance above, okay, then you could write this the following way. It would be just as valid. So again, this is something that you might want to take and star in your notes. It is quite honestly nowhere near as useful as these. These are the most useful ones because lines of charge are sort of commonplace in electricity and magnetism. So you might again want to star this and remember it. But in this situation right here, this probably is going to be useful as well. Now, just to do a variation on this and show you how this might work in different coordinates, we can take a look at the electric field above a loop of charge that has a radius of r. And there's really no functional difference between this and the ones that we did before, with the exception of what we're integrating from and to. Okay, so for example here, again, just like before, E of r is going to equal to 1 over 4 pi epsilon naught, the integral over our line, lambda dl prime, r minus r prime, divided by r minus r prime cubed. The question is, what's r and r prime? Well, instead of using x, y, and z coordinates, I'm going to use r, theta, and z. So we're using circular polar coordinates in the xy plane. And the nice thing about circular polar coordinates is that here dl is integrating along the circumference. Okay? And the circumference here is going to be r d phi prime. Okay? Now, that said, the vector r here, remember, locates our point of interest, which is here, z above the xy plane. So that's going to be z hat. And r prime locates our charge. Well, our charge is r away. It's r away, r hat. So along this entire circle, a distance of r away is where our charge lives. So here, r minus r prime is super easy. That's z hat minus r hat. Now, likewise, let's go ahead and plug this into our integral. We'll talk about limits here in a second. It's lambda dl prime r minus r prime divided by r minus r prime cubed. That's going to be the square root of r squared plus z squared. So let's raise to the 3 halves power. Well, check this out. We're not integrating over z. That's just a constant. And so what I'm seeing here is, most of the stuff here are constants, with the exception of one thing. So this takes care of all the constant stuff that can be pulled out. What we're stuck with is this integral right here. Now our limits are from 0 to 2 pi. We're going around the full circle. The thing we have to integrate is z hat minus r hat. Now, so the first one's super easy. So let me just go ahead and number them. The first one, we're integrating this. But this right here does not depend upon phi. So the constant. That's just 2 pi. Super easy. The second one, not so much. Okay, now watch. Minus r is constant. However, r hat is not. And you might be asking yourself, well, what do you mean? Why isn't it? Well, here's the answer. In Cartesian coordinates, x, y, and z are constant unit vectors. But r hat can locate anything along any sort of circular path, which means that it changes with respect to angle. And you can see that if you think of breaking r hat into components. So for example, let's think of this as r hat. We're looking down onto the xy plane. Well, its location with respect to the x-axis is this. And in truth, you could express r hat the following way. At this point right here, it is cosine along the x hat direction, and it is sine along the y hat direction. So here, r hat really is cosine of phi prime x hat plus sine of phi prime y hat. So we're going to be integrating these. Everything else here is a constant, and I just wanted to show you something before we go through anything long, because there's no reason to make it long. Now, cosines and sines are both periodic functions. So if you integrate one from 0 to 2 pi, you integrate it over a full period, you end up getting 0. And I'll show you. So here, the derivative of sine is cosine. So if you integrate cosine, you get a sine. This would be sine of phi prime evaluated from 0 to 2 pi. Well, what's sine of 2 pi? 0. What's sine of 0? 0. That's equal to 0. I want to try sine. Well, the derivative of cosine is minus sine. There's your antiderivative from 0 to 2 pi. Now, cosine of 2 pi is 1, and cosine of 0 is 1. 0. So in both cases, you get 0 here. Okay? So what that means is when you integrate in polar coordinates, the r hat unit vector from 0 to 2 pi, this is 0. Which means at the end of the day, the only bit of integral here that matters is this one right here, and that one is 2 pi z hat, right? So at the end of the day, the electric field, a distance z above our plane, is going to look like this. You have lambda r over 4 pi epsilon naught times r squared plus z squared to the 3 power. That's the stuff right here. And then you have to multiply it again by what we got when we did our integral, which was 2 pi z hat. 2 pi here is going to cancel out that and leave you a 2 there. So here you have 2, or lambda r z over 2 epsilon naught r squared plus z squared raised to the 3/2 power. And this is in the z hat direction. So this is your electric field. Okay? Now, so let's do another example. Okay, so in this problem, this is basically the same as the previous problem that we did right here, but we're actually going to integrate, instead of over a length, we're going to integrate over an area. Question is, what's the electric field above an infinite sheet of charge? Now, this is a very useful problem, and the result that we get is going to be used all throughout the electricity and also some of the magnetism section. And that's because the result from this is also the result for the electric field that you have when you're very close to the surface of a conductor. And as a consequence, we can use it to talk about the electric field that sits between the plates inside a capacitor. Now, I mentioned capacitors earlier as a method for storing electrical energy. And that's what makes this such a useful problem to look at. So just to remind you, the electric field here, if we're going to integrate over an area, looks like 1 over 4 pi epsilon naught, the integral over the area, whatever that's going to be. Sigma. Now remember, this is charge density over the area. Okay. dA vector r minus r prime divided by r minus r prime cubed. So it's the same forms, just now we're integrating over an area as opposed to a line. Now, so here though, I'd like to continue in the same venture as we did here. Here we use circular polar coordinates. And I'd like to do the same thing here. Now, the area integration for circular polar stuff looks like r dr d phi. Now, were you to integrate this, just to show you, we'll integrate r from 0 to capital R. We'll integrate phi from 0 to 2 pi. R prime dr prime d phi. The phi part gives you 2 pi. We're left doing this now. You integrate this, you get 1/2 r squared. The 1/2 kills the 2 off, giving you a pi. When you plug that in, you get pi times r squared. So as you can see, you get the area of a circle. The difference here, though, is that this is an infinite sheet. So I want the radius here to grow out to infinity. Now, circular polar coordinates are a little different than x and y. In x, you go from minus infinity to plus infinity, y from minus infinity to plus infinity to make this work. Here, we're going from 0 to infinity and then wrapping it around the origin through the angular part. And that gives us the same effect. It ends up, this integral ends up being a lot easier to do in circular polar coordinates than it does in x and y. You can still do it in x and y if you want. So let me just delete this to clear a little bit of space here. And so that said, let's talk about what r and r prime are. Now, r, remember, is the vector that locates the position that we're interested in. So that's going to be up here. We'll say z above the origin. So that's going to be z hat. R prime, though, is as before in the previous problem. It's going to be r hat, except now instead of this being a constant, giving us a circle, or a hoop rather, or a ring, this is a variable. Okay, so r minus r prime is z hat minus r prime r hat. So the electric field here is a function of r, is 1 over 4 pi epsilon naught. We are integrating the r part from 0 to infinity, and we are integrating the angular part from 0 to 2 pi. Sigma is the charge density. We're going to assume that it's uniformly spread out, so it's a constant. dA is what I pointed out earlier. That is r prime dr prime d phi prime. R minus r prime, that's z hat, minus r prime r hat. And then we're dividing it by the length of the vector cubed, which is going to be z squared plus r prime squared. Okay, so this is the integral that we need to do. And it's really 2, again, as before. We can pull the phi out. And so when I do that, that's sitting out in front. We have 2 integrals, actually 2 double integrals. The first of which is going to be, let's see, z and z prime, or z hat rather, are constants. So here's the first one, from 0 to infinity in r, and from 0 to 2 pi in phi. It looks like r prime, dr prime, d phi prime, over z prime plus r, or not z prime rather, sorry about that, z squared plus r prime squared to the 3 halves. So that's the first one right here. And then we have minus the second integral. In this one, the r hat is not constant. Nothing is constant here. Remember, r hat itself has an angular part, which is going to be good for us in this integral, because we're going to discover it's going to be 0. So again, we have r prime squared, because there's one here and one here, dr prime, d phi prime. There is an r hat here. So used to writing z prime from the previous examples. There we go. And these are the 2 integrals that we want to do. So here's number 1, and here's number 2. I'll do number 1 first. Number 1 is this right here. And what we're going to do here is we'll go ahead and do the angular part first. R doesn't depend upon phi. Nothing in here depends upon phi. So literally you're just integrating d phi. And when you do that, you get 2 pi because the boundary, or because the initial and final points of this, give you that. So you can do that if you want. That's just 2 pi. So now we're stuck doing this integral right here. And I'm going to do a substitution. The same sort of substitution that we've been doing so far because of the way the denominator looks. I'm going to call r prime z tangent of theta. Dr prime is equal to z secant squared of theta d theta. And if I plug that in here, now take a look and see what happens here. I have an r prime here. I have a dr here. I've got this going on over here. So plug that in. We'll talk about the limits here in a second. That's going to be a z tangent of theta times z secant squared of theta d theta over z squared plus z squared tangent squared of theta to the 3/2. Now, our limits here, if you take and you put in r is equal to 0, if you think about, again, the way that tangent looks, it looks like that, where this is at minus pi over 2. This infinity right here is at pi over 2, and it passes through the origin. So when r is equal to 0, theta is equal to 0. Okay? So our bottom limit doesn't change. What does change is our top limit. Tangent of theta goes to infinity at pi over 2. So if I were to plug in pi over 2 here, that's what I would get. Okay? So when this is equal to infinity, you can divide the z through. Z goes into infinity, gives you infinity left over. Your angle still is going to be pi over 2. Okay, so there's our limits. Now let's see here. In the bottom, we have a z squared. We have a z squared. You pull that out, raise to the 3/2. That gives you z cubed. You have a z here and a z here. When you handle those right there, you have 2 pi over z from that one. Integrating from 0 to pi over 2. Tangent of theta, secant squared of theta, d theta, over 1 plus tangent squared of theta to the 3/2. Now look, this right here we know is going to be secant squared. When you do this, that ends up being secant cubed. Secant squared divided by secant cubed is secant on the bottom. Tangent divided by secant is sine. So we've already done this before. So this is 2 pi over z, the integral from 0 to pi over 2 of sine of theta d theta. Okay, so here, thankfully, we know how to handle this. The derivative of sine is cosine. The derivative of cosine is minus sine. So this is going to put a minus sign out in front when we do the antiderivative, 2 pi over z. So you have a cosine of theta evaluated from, pi over 2, or from 0 to pi over 2. So when you do that, you have cosine of pi over 2, cosine is 0. Minus cosine of 0, that's 1. A minus times a minus is a plus, so this integral ends up being 2 pi over z. Okay, so that's easy enough. So this right here is 2 pi over z. Now what about this one? Okay, so let me just, for the sake of saving a little bit of writing here, let me copy that. I'm going to paste it right here. So again, if you take a look here, r hat doesn't affect R, but it does have phis in it. And as we saw from the previous example, when I integrate R hat over this from 0 to 2 pi, you get 0. The only thing that depends upon phi in here is R hat. So when I do that integral, I'm going to get 0, which means that this is 0. Okay? So check it out. This is 0, and this is what's left. So this is a lot easier to do than the other ones, in part because we already have a little bit of experience dealing with them. So now my electric field is going to look like sigma over 4 pi epsilon naught times z right here, z hat, times 2 pi over z. The z's cancel. The 2 pi cancels with this, giving me a 2 on the bottom. So the electric field that I have above an infinite sheet of charge looks like sigma over 2 epsilon naught z hat. Now this is a pretty big deal, and this is an incredibly important result. So again, you're going to want to star this in your notes. Why is this a big deal? Well, look, it doesn't depend upon distance. If you look here, our solution for this, our electric field, depends upon how high above the sheet we are. If you look here, our solution for this case, a finite line of charge, depends upon, again, how high above we are by the wire. If we look here, our solution for an infinite line of charge depends upon how high above we are the wire. So this doesn't, though. This right here only depends upon the fact that you're dealing with an infinite sheet. And what's nice about this is that as long as you stay away from the edges of a finite sheet, this equation right here works. So the electric field at all points above an infinite sheet has the same value. That's incredibly useful. So the last topic I want to talk about is something called electric dipoles. Now, I've already given you examples of dipoles before, or at least I just mentioned them. Generally, what you have is you have a region of positive and you have a region of negative, and they're connected to each other. For example, like with a rod, or if you wanted to think of, a physical example, many molecules are polar. They can act like dipoles in the presence of an electric field. So really what you have is you have these charges that are separated by a distance. Another good example of a dipole could be an atom. Okay. Now, in general, we're going to call the distance between these two right here d. Okay. Now, you can define something called the dipole moment, which it points from the negative charge to the positive charge. We're going to call this little vector here d vector. And the dipole moment, which we write as p vector, is equal to q times d vector. Now, the q here is just the magnitude of the charge. In general, when we're dealing with dipoles, for example, this might have a charge of minus q. The charge that this has is the same, it's just opposite in polarity. Okay? Now, one of the reasons why we're interested in dipoles is because if you were to, say, subject, just as an example, a gas made of atoms to an electric field, they're going to behave like dipoles. They're going to experience a torque that's going to cause them to want to line up in a particular way with the electric field. Later on, when we talk about polarization, and in specific, materials that are dielectrics, we will be talking about dipoles again. Okay, So, so if you were to think of an electric field, let's just think of a constant electric field that maybe is passing through here, like this. So here's your electric field. It's just, remember, fields are just, arrays of vectors. So here's your field like this. I'm going to call it E. It's constant again, just to make life easy. And maybe I'll place my dipole here. Let me give it a different color. I'll give it green. Here we go. So like maybe here is my dipole on one side. I have a charge. Excuse me. Here. It goes to the center like that. And then if I were to, here's another one like that. Okay. And what I'm going to do is I'm going to say that this right here, we'll call this one the negative. So this would be Q minus, and this right here is going to be Q plus. Okay. So our dipole moment here would look like this. And actually, let me, just to keep the green there, I'm going to put this beside it so you can see. It points like that. From the negative, remember, to the positive. And it looks like whatever this D distance is here times Q. Okay, like that. Now, so remember, force is equal to charge times the electric field. So when you place these charges in the presence of this electric field, what happens is they experience a force. Now, if the charge is negative, what that means is the force it experiences is in the opposite direction as the electric field. So for example, up here, with negative Q right here, it's going to experience a force this way, which I'll call F negative. This one right here is positive. Positive ones are going to experience forces in the same direction as the electric field. I'll call this one F positive. Okay? Now, our point of reference is going to be the center here. Okay? So this will be the center of our coordinate system. And what I want to do is I want to look at the torque. So here's Y, here's X, right this way. And, torque here is R cross F. Okay? Now, so we have two torques at work. We have this torque right here. We have this torque right here. This one right here that acts, just to sort of make a point here, I'll use a thicker vector. This one right here we'll call R1. So this is 1. You got another one over here. That, which we'll call R2. Okay. And R1 has a length of d over 2. That's our distance. Okay. R2 has a length of d over 2. All right. So if I look at the net torque, we're going to have 2. So sum up my torques to get the total torque. We have 2 torques, tau 1 and tau 2. Okay. Tau 1 is going to be R1 cross F negative. Tau 2 is going to be R2 cross F positive. Now remember, the only difference between F positive and F negative is the sign, right? And you can write them both in terms of the electric field. So for example, F negative here, I'm going to call minus Q, that's whatever this charge is, its absolute value, times what the electric field is. Remember, the electric field is constant. F positive is going to be positive Q times the electric field. So the forces are the same, it's just one is positive and one is negative. Now, R1 and R2 are the same, it's just they point in different directions. Okay? So here, if I were to look at torque 1 and think of it in terms of D, torque 1 here is a consequence of this. This points towards the negative charge. Now remember, here D itself is defined as pointing from negative to positive. So from a directional standpoint, R1 as a vector would be minus D vector over 2. From a directional standpoint, R2 would be, since it points from negative to positive, points in that direction, would just be D over 2. So torque 1 here would equal to minus D over 2 vector cross minus QE. Torque 2 is equal to R2 cross F positive D over 2 cross Q times E. Now look, this is a negative, they cancel. So these are the same. So our total torque on this dipole would be tau 1 plus tau 2, or D vector over 2 cross Q times E plus D vector over 2 cross Q times E. But look, Q is just a number, you know. This 1/2, they're the same, so this is going to be a 1/2 plus a 1/2 plus a 1. So what I'm going to do is I'm going to pull a Q over here in front of the D. And this is our dipole moment P. So if I want to know what the torque is on a dipole, it's going to be whatever the dipole moment is. Whatever the dipole moment is, cross the electric field. And that's what makes it want to rotate. And as you can see here, if this thing is free to rotate, what happens is it's going to want to line up with the electric field. Okay? Now this has consequences. You know, I'll just briefly talk about them. And that's that when this lines up with the electric field, when this moves this way and this moves this way, what you end up with is two charges with a field that points from the positive to the negative, like this. And what this does is to take away from the overall uniform electric field that's moving through here. Now, as we're going to see later on, this is going to have a consequence whenever we talk about dielectrics. And that's it for this video, and I'll see you in Chapter 6.